Let's talk about graphs of secant and cosecant, because there are some interesting things that we can get out of here. First, I want to look at this basic relationship. I want to look at y equals x and the relationship between the graph of y equals x and the graph of its reciprocal y equals 1 over x. The secant and cosecant are reciprocals of cosine and sine. What we want to look at is what happens when x is getting close to 0, and then what happens when x is getting very large. So what we notice is happening when x is getting closer to 0, as x is getting closer to the 0, the reciprocal is getting larger. And if we zoom out, the closer we are to 0, the larger values of x we get. It's really hard to trace. Oops. But I can't even land on it. Oh well. So the idea is that when x is getting small, its reciprocal is getting large. Moreover, when x is getting close to 0, its reciprocal is getting close to infinity. It's 1 over 1,000, 1 over 10,000, 1 over 1,000,000, 1 over 1,000,000,000, 1 over 1,000,000,000,000, and so on. That number is getting very, very small. In the other direction, when x is getting very large, 1 over x is getting very small. For the same reason. When x is 1,000,000,000,000, 1 over 1,000,000,000 is very small. So when a number is getting close to 0, its reciprocal is getting close to infinity. Let's take a look at a graph of sine. And then let's take a look at a graph of cosecant. The sine and cosecant are reciprocals. So notice that every time sine is getting close to 0, cosecant has a vertical asymptote. Sine of 0 is 0, so cosecant of 0 is undefined. Here's the graph of x equals 0. Whenever sine is 0, cosecant is undefined. And that's what was happening in that graph. When a value gets close to 0, its reciprocal heads off towards infinity. The graph of cosecant and sine do run into each other, because if sine of pi over 2 were equal to 1, and the reciprocal of 1 is 1. So that's where the graph of cosecant and sine are going to meet up. They agree on that one value, because 1 is the reciprocal of 1. If I change the amplitude of sine to 2, that makes that vertical stretch. We still get these vertical asymptotes when sine is getting close to 0. But now they agree on the value of 2. If I start shifting things around, now sine is equal to 0 when x is equal to 1. And so that's where cosecant is going towards infinity. Yes. Yes. So the 2 pi is so there's another place where sine is equal to 0 at 2 pi. There's another one. Or if we were doing this in degrees, that would be at 180 and 360. So wherever sine is equal to 0, we see cosecant headed off towards infinity, because cosecant is the reciprocal. This is what people are talking about when they say dumb things like 1 divided by 0 is infinity. because as sine of x gets close to 0, cosecant is going towards infinity or negative infinity. Are infinity and negative infinity at the same place? It's kind of like a wraparound. It's like you go up here and it goes, you go through a little warp Mario style. It's like a little warp. Same thing, we can do the same thing with cosine and secant. Tangent is a little bit different. That one's cosine. Let's take a look at what's going on with tangent. Remember, tangent, why did it make it? Don't just copy the numbers. Look, I made a red and a blue. Obviously, I want purple next. There. Come on, Desmos, get it together. So tangent is sine divided by cosine. Tangent is sine divided by cosine. Tangent is sine divided by cosine. So tangent has these vertical asymptotes when cosine, the denominator, is equal to 0. So cosine is the red graph. So when the red graph is getting close to 0, like, or is equaling 0, like here at pi over 2, that's when we have a vertical asymptote on tangent. Now it's making everything purple. Maybe I'm overthinking it. So tangent is sine over cosine. So when cosine is negative, that's when tangent is throwing a vertical asymptote. Because as cosine gets close to 0, tangent gets larger and larger and larger. This is regardless of the value of sine, because sine is headed towards 1 and cosine is headed towards 0. And 1 divided by 0 will head towards infinity. Think about the shares of Ocean's 11. And what happens to the shares of Ocean's 11 as they go to Ocean's 10, and then Ocean's 9, and then Ocean's 1, and then Ocean's 1/2, and so on. Sure, here you go. Okay. It depends on what you think of, what want to think of with with real life and how you interpret those things. Depends on what kind of function you're using to model certain things. I'm not really an expert on real life. I'm just the expert on mathematical models. I wish I had a good example of some kind of asymptote. Nah, because eventually the rabbit population would consume all the resources and then drop to 0, drop back down to 0. So on a long enough timeline, there is a horizontal asymptote. That one makes a little bit more sense. It certainly tries to be. So vertical, that's difficult to say, but like if we think of, let's see. So let's take a function, sine of x minus 2, and let's now if I make the amplitude 3, right? The amplitude up and down. Top is 3, bottom is -3. Actually, let's change to cosine. I want one that starts at the top. Right, here's the top 3. Top is 3. Oh, I made it 5. Top is at 5. Now let's change my amplitude to a function. Is this gonna do what I want it to do? I think I made things too big. Oh, I made it increasing. So here I've got a cosine graph, and we can see the oscillation. We can see it going up and down, but our amplitude is all jacked up, right? Our amplitude keeps getting bigger as we go away from zero. Now, if I put the top and bottom, the top is going to be 1/3 x minus 1. And the bottom will be approximately the opposite of this. Now you might be thinking, these aren't exactly at the top and the bottom. This is because the cosine is still adding stuff to this. The cosine is still adding stuff to this. So if I drop off this extra 2, now I'm where we need to be. Now I'm landing right at the top and bottom. If I shift this up by 2, if I shift the top up by 2 and the bottom up by 2, now they're right where they need to be. So here we're seeing kind of some long run behavior. Now where we might see something different, get these off, is if we think of the function y equals, is this going to be too much, too extreme? Yeah, it's a little bit extreme. There we go. Stretch things out a little bit. Now what we can see is that in the long run, we're getting this cosine behavior up and down and up and down. But instead of having a fixed amplitude where the top is always at 1, the bottom is always at -1 or 10 or -10 in this case, the top is at 10 over x and the bottom is at -10 over x. And we can see all the points that we expect at the top and bottom. So in this case, if we zoom out, we'll see a horizontal asymptote at 0 because the top and bottom are headed towards 0. 10 divided by x, when x gets larger, will tend towards 0. So here we have a horizontal asymptote. This is like long run. Any questions? Comments? Rabbits were a very interesting invasive species in Australia. There's a huge rabbit problem in Australia. Someone brought some rabbits. And apparently, none of the natural predators in Australia enjoyed rabbits. So I go, what's this? Oh, that's disgusting. I'm not eating that. And I go, hey, those new little rodents that are running around with the ears. Yeah, I was going to eat one. It looked tasty. I go, they are not. And so all the predators are like, oh, well, we ain't eating those. And the rabbits just did what rabbits do. Rabbits' only natural defense is like, oh, we need a defense. What are we going to use? More rabbits. And so it kind of grew unchecked, and it was kind of a problem. Yes. Okay. All right. That's going to do it for today. I will see you all on Thursday. Everybody have a good couple of days, and thanks for playing.